Hello everybody, welcome to Statistics and Theory. This is Dr. Vahid Aryadoost. In this video I am going to demonstrate how to do factorial ANOVA with interaction analysis. It's a rainy day in Singapore, so please expect to hear some background noise, especially clapping thunders, which are pretty common nowadays during this season, this rainy season in Singapore. Anyway, so in the video I am going to discuss 8 things. I start off by talking about data visualization, which is the first step to the analysis. Then I will discuss the 2 assumptions of ANOVA, 2 major assumptions. There are other assumptions too, but these 2 are the most important ones. Normality of residuals and or normality of the data. Assumption 2 is the homogeneity of variances. I'm going to use Levine's test of homogeneity and Bartlett's test. I will show you how to run both of them in RStudio, and then I will run the ANOVA itself. There will be 4 types of ANOVA. One is one-way ANOVA, then 2-way, 3-way, and also another one including interaction. It's still a 3-way ANOVA, but it includes interactions among the variables. Then I will talk about model fit, and I will shed light on AICwt, or the weight of AIC, as well as BICwt, or the weight of BIC. Then I'll discuss the effect sizes, in which I'll demonstrate how to compute 3 types of effect sizes: eta squared and its partial version, omega squared and epsilon squared, and then finally I discuss doing post-hoc analysis. I'll shed light on quite a few types of post-hoc analysis which are common and show you how to visualize post-hoc results in the form of a table. So first things first, if you have not watched my previous videos, please go to my channel and watch Getting Started with RStudio and R if you're not familiar with R and if you have never used R before. There are 5 videos altogether in this list, which I think are quite useful for beginners. The previous one, which I released, is about independent samples, t-test, Levine's test, etc. The next thing that I would like to recommend to you is the ANOVA videos that I have created, and these videos are around 7 of them. So in the current video, I do not go into too much details about how to interpret the results of ANOVA because I've already covered them in this series of videos. I will also leave this link for you to go through them. You know, for example, in the last video, I have discussed how to report the results of factorial ANOVA. It actually applies to the current video as well because the principles are going to be the same. So let's get started with our factorial ANOVA analysis. The first thing that you need to do is, and yeah, that's the first thunder. I don't know if you heard it or not, but it was pretty loud. Anyway, so the first thing that we need to do is to open our data set. I've already done that. It's called ANOVA. And you can actually download this simulated data set. It's not real. Let me show you where you can download it. It's in my GitHub account. You need to click on this Excel sheet and you download it, and also the codes that I'm going to use in this video can be downloaded from this this part of the GitHub account, and so you can just step by step follow me if you're interested to simultaneously watch the video and run the analysis together with me. So the data is here. The independent variables are 3. Gender, which is represented as gen2, is a string variable here. Male is represented as M and female as F. There is another numerical variable, just is exactly the same thing, but we have used numerals. 1 stands for males, etc. So I'm going to just use gen2 because it's a string variable, and based on my experience, you would not receive any error messages if you use string variables in ANOVA. We've got first language. Participants have been divided into 2 groups, English and non-English as first languages. And socioeconomic status, we've got low, mid, and high. Using these 3 independent variables, I'm interested to predict grade, which is some kind of fictitious score that students have received on some fictitious test. So let's get started with analysis. What I would like to do first is to close this and quickly open the data set for you, and just to see how you can open it. You see, I have done this before in other videos, so I don't go into too much details. This is it. So the data set is correct, as I showed you before. So I click on import and it's imported, and an R object is created on the right hand side here, indicating that, well, your data set or data frame is fine. Now let's get started with data visualization first. I want to take a look at the content of the data first. Yeah, the content is okay, as you see. You just run this code. It's head and the name of the data frame. And the content is fine, as I said. It's gender, first language, and grade, and SES as well. The second thing we need to do is to call library ggplot2. If you have not installed ggplot2, you should. In previous videos, I have discussed how to install packages or tools on in R, so I don't go through details. Just use this code, library and ggplot2, and hit Control Enter on your keyboard. It will be open. Now let's go through the analysis. First, I highly recommend that you look at the density plots of your data, because it gives you a clear visual understanding of how the data is distributed. The first thing I want to generate is going to be called P1. Again, since I have discussed how to generate plots in R, I don't go through too much detail, so you can just run this code, and if you need more information, please watch my previous videos. So let's run the first one. Now P1 as an object has been created on the right hand side. You see P1 has been created. Let's open P1, which is basically a ggplot. So I'm going to hit Control and Enter, and on this side it appears. You can zoom and you can inspect it visually. On the horizontal axis, we've got grades. That's the dependent variables, and then the density of the grades on the right hand side, on the vertical axis. Okay, so those students or people who have who have a high SES background are represented by this pink color, and as you see, the mean might be around here, which is way above the test scores of the students who are coming from the low and mid class. Because if the mean of this group of people is right here, the mean of the mid SES group is around here, is where it peaks, and the mean of the low SES group will be around here. It's the green one, which is being superimposed by the other two groups. Okay, so it was around here. My visual inspection indicates that there should be some differences between the three means of the three groups, but as to whether this difference is statistically significant or not is a different question. We can test that later. So in the same way, you can generate ggplot this time around for gender, and there we go. You can zoom in, and you see that the two mean scores are probably different, or they may or may not be different. I don't know really, but we should look into that in our ANOVA analysis. The next one is the ggplot for first language. This thunder was very loud. You probably have heard it this time around. Anyway, so let's run this one, and let's open it. Yeah, this is the ggplot for first language. So in conclusion, there are three independent variables. As you saw, one of them has got 3 levels, SES, and the other two have got 2 levels. Now, you can, in the same way, you can also generate box plots. You can first open the ggpub_r, and I did it, and then run this code to get box plots and P4, yeah. And this is the box plot. This line, as you know, is the median, so it indicates that the median of high is the high SES is above the rest of them, and this is just in line with the previous observation that we had. So the second one for SES and grade is a different color theme sort of box plot. So yeah, this is, just really the colors are different. If you like to arrange all of these graphs into one panel, you can run this code and wait for a second. Yeah, everything will be beautifully organized in one panel for you. So if you want to use them for publication, it's just publication ready. Now, getting started with ANOVA, we should first look into the assumptions of ANOVA. As you know, the first assumption is normality. Now, normality can be defined in two ways. Many people, especially in applied linguistics, assume that normality refers to the normality of the data, whereas if you look at statistics and psychology research, basically normality refers to the normality of residuals. I'm going to run both of them, and if you're asking me which one is the best, I would say, well, it depends on your discipline, but the actual assumption is the normality of residuals. That's the thing that we need to investigate and also report. So the first thing is to call psych library to be able to get the normality statistics for the data. So I'm going to open it, and using the describe code, I will generate means and skewness and kurtosis, etc. The two things that are necessary here are the skewness and kurtosis statistics. Skewness is 0.8. This is for gender. We shouldn't read that actually. Go directly to the dependent variable and look at the statistics for it. The skewness statistics for the dependent variable is minus 0.36, and the kurtosis value is minus 0.41. They indicate that the data in the independent variable is very well normally distributed because it falls between -1 + 1 or -2 + 2. In those previous videos that I mentioned before, I have explained how to interpret skewness and kurtosis, so I don't go into too much detail. Really, there's a lot of literature around how to interpret skewness and kurtosis. But generally speaking, this data shows that my sample is fine, and I can go ahead and run the analysis. The next thing that we can do is to look at the residuals, whether the residual is normally distributed or not. So you should either do this or that. To me, I think the residual will be the best thing to look into. So using this code, I'm going to generate an object called res underline AOV. And how do I generate it? Is AOV brackets, then grade, then one of the data that I want to test grades against, and one of the variables, and this variable is SES2. My data is ANOVA. That's the Excel sheet that I'm going to use. So let's run this code, and you see immediately this object was created. You can click on it and open it. It will be open, and some information is available here. It tells you what this file includes, etc. So it's not a very necessary thing to go through at this time. So I just want to open it in this panel, in the console panel. So I'm going to run this small code here, Control and Enter, and it opens it for me. You see it includes residuals, and there is a high amount of residual here. And I'm just curious as to whether this residual deviates from normality assumptions or not. It's the residual of SES2. And in the same way, you can run the residuals of gender and residuals of first language. Just feel free to replace them with gender and first language. Okay, so in order to find out whether this residual deviates from normality or not, we need to create histograms of them, or we could create a QQ plot, or we can run a Shapiro-Wilk test to figure out whether they are normal distributed or not. So first things first, let's do a histogram. So hist, and then the name of the residual file which I created. You see, as I highlight this, these are encapsulated in, become encapsulated in boxes, then at sign residuals. So you have to include this. So let's run this. Very good. This histogram is generated. If you zoom in, you'll you'll see that the data is relatively normal. It's slightly positively skewed because the leg goes to the right hand side, so it's slightly positively skewed, but I don't think that that's a big cause for concern. I close this and I then generate a QQ plot. I have to first open library car, CAR, and I'm gonna hit Control Enter on the keyboard. The library is open, as you see here at the bottom. Then the code is going to be run. So the object I'm going to generate is called QQ. As I have discussed in previous videos, whenever we have got this smaller than and hyphen sign, it indicates that R should create this for us. So QQ plot, then residual res hyphen AOV, then residuals, and ID is false, so we don't want to see the IDs. Okay, IDs of people. So let's run this, and we will get the QQ plot. The line in blue here represents normal distribution, and those lines on both sides and the shaded area represent 95 confidence interval. So if any data set falls outside, any data point falls outside of this shaded area, they are not very normally distributed. So they deviate from the assumption of normality. On top of this figure, and also around here at the bottom and a little bit in the middle, we have some minor deviations from normality. I personally do not think that this is a very big cause for concern, because the deviations are not too much. If you like to see who these people are, you can change false to true. We can give it a try, see if we can get the IDs of those people or not. Yes, so we got some IDs. It's just number 42 and 43. You know, only these two numbers have been generated for us. Yeah, unfortunately not the rest of the numbers are not very clear, but I would go through the data and I would probably remove 42 and 43 and rerun the analysis. Hopefully the data will be more normally distributed. Anyway, now Shapiro-Wilk test is basically a formal test of normality. In this case, we're going to run it on residuals. But a caveat concerning Shapiro-Wilk test is it will be very sensitive to the sample size. So that's why a lot of people do not use it and just rely on visual inspections or skewness and kurtosis. But we can run it. Yeah, as I said, you know, it's very sensitive, so the p-value is very high, very low. It indicates that the data is not normally distributed, but I think there is enough evidence to convince me that, with the exception of this test, that the data is probably normally distributed. So let's move on to the homogeneity of variances assumption. I'm going to run two tests quickly. Levine's test of homogeneity, which I have explained in just the previous video on R, and Bartlett's test. Levine's test is usually suitable for scenarios in which we've got several levels of independent variables. And so if you run this, you may get a warning message. Levine's test is run in this way: Levine, then T, capital T test, your dependent variable separated by tilde from the independent variable on which you want to run the analysis, and then the data set separated by comma. So let me run this. Okay, this is the warning message. It's not an error, as I said before, because the group has got only two sections or two, let's say, subsets. One is females and another one is males. Overall, as indicated by the p-value here, this PR stands for probability. We have strong evidence that the homogeneity of variances has not been violated across gender, so it's good news for us. Now I want to include all of the variables. Gender, asterisk, first language, asterisk, SES, and then data set. This is how you include multiple independent variables into the analysis. Nothing else really. So control and enter, and then I will get the results of this analysis as well. So the probability or the PR or the p-value is extremely small. It has been indicated by 3 asterisks, and this is the scientific notation of it. It's really small. It's almost 0. It's very close to 0, as you see by this notation at the bottom. So this indicates that there is some violation of the homogeneity of variances, but we can further go ahead and do Bartlett test of homogeneity of variances to see if we can get the same results. So sorry, I need to run this again. Yeah, okay, I ran the code. The Bartlett test is done in exactly the same way as Levine's test is done, with the exception that it has got a dot in between the word Bartlett and the word test. The codes are the same, and it indicates that there is no deviation from from the homogeneity of variances in terms of gender. But what if we include all of the variables? Now, there is a difference between the code here and the previous code of Levine's. You got to include interaction, then gender, then brackets, then gender, comma, the second independent variable, comma, the third independent variable, then brackets and comma, and you close it. Make sure that the code is used in exactly the same format, otherwise you will receive an error message. So let me hit Control and Enter on the keyboard and get the p-value. The p-value is still statistically significant, so we have some deviations from the homogeneity of variances. What should we do under these circumstances? There are 2 solutions. Number 1, you can just go ahead and run your Anova test, because some people believe, actually a lot of people believe that Anova is quite robust against even some deviations from these assumptions. But the second one, which will be a safer way of doing things, is to stop here and do a non-parametric test. But that is gonna be discussed in a separate video. In this video, I just want to go ahead, I just want to pretend that there is no deviation from the homogeneity of variances assumption and run the Anova test for you, because this is really an illustration based on simulated data. Okay, so let's get started with Anova tests. I'm going to run 4 tests for you. First of all, Anova.1. This is an object that I want to create in R. And the reason why I want to differentiate this object from the rest of the objects that I will create is that I want to create one object per one analysis. So one-way Anova will be representative of the one-way Anova test. Then the two-way object is representative of the two-way Anova test, and so on and so forth. So three-way Anova and the interaction-based Anova, I have separate names. So let's first run the one-way Anova test. Okay, I ran it, and as you see in this side, on the right-hand side, the one-way Anova or one-way object has been created for me. Now I want to open it, and I want to open it actually in the console to see what I've got inside that.